In this particular video, we're going to be discussing the applications to general relativity, and which are black holes and gravitational waves. Now, the big ideas out of this presentation is that we were able to see how one soldier in the Russian front was able to solve Einstein's equations for a small, spherical, compact object. And this would be the black hole. And the research involving black holes were pioneered by Sir Roger Penrose, who recently won the Nobel Prize in 2020 for his findings back in 1964, and Stephen Hawking. By 1916, Einstein would think of a consequence of his general relativity theory, which would be the fact that if you curve the landscape of space-time, then it can surely ripple like ocean waves. So the directions to take to general relativity, because it is a theory of gravity, all the applications and directions are more based on astronomy and cosmology. But back in 1915, in November 11th of that year, Albert Einstein would present his final result to the Prussian Academy in Berlin. And not only was his generalizations not only did that generalize his 1905 special relativity theory, it can also describe several astronomical events such as Mercury's eccentric orbit. And as a modern theory of gravity, you can also describe the source gravity of various planets and stars, provided that they have some particular rotation. And you can call that weak and strong gravities. And like I said, since gravity is described geometrically as inward warpings, then you can surely ripple space-time like an ocean wave. Now, to help us along with this, let's consider one more piece of mathematics that's called linearization. So just as we take two vectors and we put them into a dot product and we get a scalar out of that, you can take two tensors, put these two tensors into an inner product, and the product that comes out of it is a scalar. And so you can take any two vectors and you put them in the inner product and you get a scalar. But more specifically, if you have an inner product between any tensor and a metric tensor, and it has to be ordered in this way. It has to be ordered this way because you have the mu-nu components that would cancel out, and from this result you can get an eigenvalue constant, an eigenvalue scalar A, which is that of the second tensor. Now, the reason why is called a linearization process. This metric tensor is really, it has a diagonal. If you think of it as a matrix, it has a diagonal of all these ones, and the other components are just zeros. So you take that diagonal and you multiply that with the other tensor that has all these other components. You only consider that diagonal to where all the summations of all of these diagonal terms, they become a singular scalar result, and that is called the eigenvalue. And if you don't know what an eigenvalue is, and this is your first time hearing it, eigen in German means self, so it's a self-value. And a self-value of a matrix that has all these different entries, and you need to describe, you would want to describe all these different numbers as a singular number, a self-value. And so if you take a tensor with all these different components, too much that we actually care for, all we need is just one constant out of the entire tensor, and that is the eigenvalue of that tensor. So with that said, we could go ahead and look at Einstein's equations, and we linearize both sides here on the left-hand side and on the right-hand side. And for the left-hand side, we just have the minus Ricci curvature. The Ricci curvature meaning that it is the numerical value of the actual warpings from the source mass. And on the right-hand side, we get this eigenvalue to be really based on the source mass and based on the gravitational, the Newtonian gravitational field, and also its torsion, its rotation. And so putting these together, we get an equation, a single equation based on source mass, on rotational speeds, and most importantly, the depth of this curvature source. And as we can see here, as v approaches c, so if we have a violently spinning object, then with the increasing torsion, that deepens the source curvature, meaning that it is strengthening the gravity of that object that's spinning. And so now we could consider using linearization and consider what will be black holes and gravitational waves. So between 1914 and 1918, Germany was in the First World War. By 1915, just barely a month after Einstein publishes general relativity, a German soldier in the Russian front named Karl Schwarzschild, he sends Einstein a letter, and the letter contains the first solution to the general relativity equations. Now, Schwarzschild, he's not just some regular average Joe. He was an astronomer, a physicist, and a mathematician. So that would explain his promptness in finding a solution so quick after a short release. But he was drafted to the German Imperial Army, and that's why he's in the Russian front. Now, his solution considered a supermassive, very dense, compact object whose total curvature is so deep, not even light can escape it. And as you would know already, this dense, compact object, Schwarzschild's solution was for a black hole. And to go a bit off topic, Schwarzschild is a combination of two German words, Schwarz and Schild, which means black shield. And I find it very fitting that Schwarzschild found a solution for a black hole. And you can think of a black hole as this black shield upon the space-time. And so according to an outside observer who is looking at this entire black hole, it's looking at a spherical geodesic. It's looking at all the spherical components of this object. And it does depend on certain parameters up front. Certainly this one for the time, and this one for the length. This d omega squared, that's all the angular dependencies squashed together. And let's consider this speed to be some gravitational escape velocity, 2gm over r. Now, due to the fact that black holes are inescapable, especially to light, we need to consider that these black holes have a boundary. And this boundary is the moment at space-time where time is permanently frozen and space is compressed down to a pinpoint called a singularity. So this boundary, the last location of when and where you see free-falling objects, that is called the event horizon. And within this event horizon is the dark shadow of extremely warped space-time. The radius that spans from the geometric center of the black hole to the edge of the horizon, that radius is called the Schwarzschild radius, and that can easily be derived through the metric and replacing v squared as the escape velocity. And surely enough, we can solve for the Schwarzschild radius as given here. Now, this radius, it does, of course, depend on the mass of the black hole, but it is also affected by these constants g and c squared. Now, because of where they're situated in this equation, the Schwarzschild radius is always smaller in magnitude than the black hole mass itself. So because of that, black holes are deceptively small for their super duper masses. And that is most absolutely the case For instance, the center of our Milky Way, the other half of the Nobel Prize project, the mass was discovered to be 400 million times the mass of the sun. However, the size is only 14 suns across in diameter. So considering that you have 14 suns in diameter, within that sphere you have 400 million solar masses. That is a whole lot of mass in such a small area. And these Schwarzschild radii they're boundaries of no return for this light, and that's proven by Roger Penrose in 1964, and that is what helped him win his half of the Nobel Prize. Now, Stephen Hawking, he never won the Nobel Prize, sadly. His work is just purely theoretical with no experimental backup. But until the 1970s, scientists believed that black holes are continuously growing while taking in all this light and material. But we still don't know what's happening inside these black holes. If you have black holes taking in all this stuff, it's going to be increasing its entropy. And entropy is just a matter of disorder. So if it takes in all of this material and all the light, it's increasing in disorder. And it is desired to have some order, especially if you have a black hole that's cold. You can't have maximum entropy if you have a cold system. You have to have order. So in order for a black hole to regulate itself, to maintain the entropy, then whatever excess entropy that the black hole has, it will be released as radiation from the horizon, from the surface of the black hole, and that is called the Hawking radiation here. Now it's almost made of constants. What is variable is the temperature and the mass, and as you can see that they are inversely related to each other. And if we do solve for the temperature of the black hole, which is here, so we could go ahead and move this constant up on the other side, the supermassive black holes, the very large black holes, are cold. And you have the smaller black holes that there are hot. So because, that also throws in another question about what is really happening inside. So cold systems means that all the objects inside, they're not doing anything. But because black holes they're black, you really don't know what's really happening inside, and there's no way to shine light in it. It's just gonna be eaten in. So you gotta wait until the black hole gets small, so that it can emit some heat, and you can have some idea what's going on inside. But since it's a small black hole, how can you fit inside a small surface? So it really keeps black holes an enigma and very interesting topics in astronomy and in physics. Now the second part of this presentation is the gravitational waves. And we can definitely use our linearization mathematical tricks in this concept, because we're taking Einstein's equations and we're making a wave equation out of it, similar to what Maxwell did with the Ampere laws and the Faraday laws, So we could go ahead and use Einstein's equation using the gradient equivalence here, and we linearize both sides here and here. Focusing on the left-hand side, all of this trickles down to the fact that we have this ripple function acting on this operator. And this operator here is called the D'Alembert wave operator. And this function here is the ripple function, which tells us what the ripple of space-time looks like, and it acts as a wave function. And now let's consider the fact that these waves are either out in the vacuum with no mass around it, or that they were induced by astronomical masses. So let's consider the fact that there's no mass around it. That linearizes the source energy tensor as 0, because if you have no source mass, you have no source energy density. So you go that down to 0. We get an equation that looks like an electromagnetic wave. But instead of an electric field or magnetic field, we have this ripple function. Now this says that gravity is not electromagnetic at all means, but what this is saying is that we have gravitational waves that are moving at the speed of light. So you could make the analogy that gravitational waves are just like EM radiation waves, like light waves. But there is a difference between the fact that you have a gravity wave and a light wave, and there is differences in those similarities here. But we could definitely describe a ripple function as a sine wave. Positive time for the forward arrow of time, and we have minus r to keep up with that with the anti-parallel axes of space and time. Now let's also consider the fact that these gravitational waves come from these astronomical sources. So more specifically, the gravitational waves that were detected in 2016, that they came from 2 colliding black holes. So there must be, of course, some source. Let's call this source rho sub e, and that is just the source energy density, E over V, and it must be acting on the same ripple function. So we have a wave equation that looks slightly different than before. And believe it or not, it is harder to solve analytically, especially if this rho sub E is not constant. And that is most certainly the case with black hole collisions, where you have 2 black holes and they're spiraling in, they're warping the space-time, they're rippling it, and all of a sudden they collide. At that moment of collision, you have the 2 sums, you have the 2 masses that are not even added together to get the total sum. You get a weird mass called the chirp mass, and that's what sends that final pulse. And then by the time you have that final black hole, by the time the wave propagates out, that mass is not even the first 2 masses added together. It is some of that mass is lost through E is equal to mc squared. So you have no constant energy density, it's variable. So because of that, scientists rely on numerical simulations called numerical relativity, and they of course depend on the detectors. So if you look at the image beside, you see that this wave is not really a proper sine wave. It looks unique. It looks squashed at the moment of the pulse, and then it just levels out. So this is not a proper pure wave that we could solve through mathematics. It must be solved through numerical simulation. But let's consider the fact that if we have gravitational waves, just as we have photons in light waves, do we have a particle in a gravitational wave? And let's consider that possibility. So if gravitational waves ever have a particle inside it, it will be called the graviton. The graviton is one of those particles that it's only predicted. It's been predicted since the 1930s, and technically 1933 by 2 Soviet scientists. I know this because I did independent study on the graviton. But even if the gravitational waves were detected back in 2016, not one had been detected. Not one graviton has been detected. So it's a question whether or not there is a graviton inside these waves. Well, let's go ahead and consider that fact, and let's play with the math. If there is a graviton inside the gravitational wave, then there is indeed an energy density, and let's call this a detection likelihood. If you have wider propagations of a wave, so more coverage of a wave, that means one little particle of gravity must be within this large length, which is very hard to extract, especially if you don't know where that particle is. So if you have a longer and longer propagation of a wave, this graviton has increased distribution of where it would be. So this is called increased probability density, probability of where it would be. And since it has a lot of coverage, it has an increased distribution, so less likelihood to be picked at any of these locations. So we could describe the energy density as such here, and of course R here is to the 4th power. And if we consider a wavelength of a gravitational wave to be 10 to the 16, put that to the 4th power, and that's a very large number. And if it's in the denominator already, you have a small number. The likelihood of detecting a graviton is near 0. And that is keeping up with what's going on because we don't find any gravitons. So this is telling some truth here. But we go ahead and put this into the equation, and what we get is something unique and very promising. This term right here, this is area, and not just any area. According to loop quantum gravity, which is one of these quantum gravity theories, this area here is the surface area of a quantum chunk of space-time. So it promises that gravitons exist. This equation promises that gravitons exist in the wave, but it's still hard. It's still tricky to solve because we got this term here, and this term can be equal to 0. What this value is, this is called the spin quantum number, which gives the idea that we have a rotating particle as if we have a rotating planet around an orbit. But the weirdness of quantum mechanics suggests that it's not really rotating. We just call it that just to mess with you. But let's consider the fact that it is, quote, spinning. If you have an m sub f sub 0, the entire left-hand side here is 0, which means somewhere in the right-hand side is 0. It can't be the area. The 1 over 4 r squared, well, if r is large, then sure, that could be equal to 0. But n, this eta function, this ripple function, that could also be equal to 0. But since the ripple function is about the gravitational wave, how could you have a wave with a 0 ripple function? That makes no sense. That is also giving gravitons that same enigma status as black holes. But if we were able to extract gravitons from these waves, then it's a step closer to understanding quantum gravity, which is one of our most important questions in physics today.